So yeah, my name's Eric, and yeah, we'll get right into this. Basically, we'll do a whole whirlwind tour of in-vehicle networks and how you can get on them and play around with them, and then hopefully get you out of time for lunch. So yeah, that's the goal. So this is all going to be about this thing called CAN bus. What the heck is CAN? Stands for Controller Area Network, and it's pretty much just the networking that's used in all cars now. Why? Mostly because it's cheap, and it's also really integrated into a lot of controllers out there. So you can buy a microcontroller that has multiple CAN controllers inside of it that actually do the physical layer stuff, and they're cheap. So the automotive companies like to shave pennies, so they've continued to use this this CAN bus thing. It's also rather reliable. You know, there's a CRC built in on the wire, so at the hardware level, it's kind of nice. So there's a lot of types of CAN bus you'll see. In automotive, the main ones are high speed and low speed. Difference being high speed, it's a differential signal, so you get some noise immunity there, two twisted pairs, kind of like Ethernet. And then the low speed is a single wire, which is just one wire and ground. And that's used for things that are even cheaper, like lights and switches and things you don't really care about that much if they go wrong. Fault-tolerant CAN is something that's kind of a neat hack. It's basically the high-speed one, but if you cut one wire, it becomes the low-speed one. That's used in airbags mostly. And CAN FD is this new flexible data CAN that's going to address some of the limitations of CAN, but nobody uses it yet, so whatever. The setup in a car looks something like this picture. So you'll have multiple different buses chained off of each other. For example, you might have a high-speed network with your engine control, transmission, body control, anti-lock brakes, things that you really care about. And then one of the controllers will act as a gateway, almost like a router in a way, to send messages back and forth to a separate bus for the lower priority things, maybe your instrument cluster, your door control modules. And there really are this many controllers in cars nowadays. Like, they pretty much are computers for all intents and purposes. There's no mechanical linkage between the pedal on a modern car and the engine. It's just all electronics. So why might you care about CAN? It's used in a lot of stuff, not just cars. Industrial control systems, SCADA systems, all that is often using CAN for just certain industries prefer it. Pretty much every car, like I said. And also, apparently planes use it. So, I mean, if you wanted to, you know, get on a 777 and plug into something under the seat, maybe maybe you'll find something. I wouldn't recommend it, though. It's a direct interface with the controllers, and this is really the key for the automotive world, is there's not many other ways you can directly talk to a controller in a car. You might have like some weird button press sequence that gets you to a maintenance like menu, but that's about it. So this is actually, you know, you're sending messages straight into a controller, and it's actually going to interpret what you're saying. And it's pretty accessible. That connector there plugs into a plug like this. And on modern cars, anything past 2008, there will be at least one CAN bus on that thing. Some manufacturers give you more, which is nice of them. So we'll just talk about the protocol itself so we can understand this stuff. Basically, you have a bus, and this is just a bunch of controllers that are, you know, connected together. Usually it's high speed, which would mean, you know, differential, twisted pair, and just whatever wire they had lying around in a wiring harness. And then on that bus, you'll have frames. So these are sort of the lowest level packet of CAN. And really, they consist of three main things. An identifier, which is just, you know, what is this message? It has an identifier. A data length code, which just says how many bytes of data are in it, up to 8, so 0 to 8. And then data, which is actually your 0 to 8 bytes. It's pretty simple. It looks like that. So the identifier, again, is some of this 11 or 29-bit ID. Data length code's 4 bits of 0 to 8, and then your data. And that's really on the wire all that, from a software point of view, all that it is. It's nice and simple. And this brings us to the first really easy thing that you can do if you're on a CAN bus, which is a denial of service. The reason being, the way that CAN works, and one nice thing about it, is it's multi-master. So if you take a controller off the bus, it will still work. There's no one master control. So the arbitration is done at a hardware level, and the way it works is whoever has the lowest CAN ID just wins the arbitration and gets to send their stuff. Which means that you can do something like this. Just, you know, forever send the ID 0, and in cars this will actually cause some pretty bad things to happen. I've done it by accident once. It set every single fault code on the car, like all the lights just came up and the check engine, service stable track, service. It's not a good idea. I wouldn't recommend it, but it's really the simplest thing you can do. So it's fun to mention. But some more useful things come into how CAN's actually used in a vehicle. So when you're driving your car around, there's just a bunch of these messages flying around all the time. And we'll just take a look at one contrived message to get a feel for how that works. And it's pretty obvious how this could expand to all the different things that need to be sent between controllers. So in this case, you have an engine control module that's going to be taking a pedal request, figuring out what to do with your engine and all that stuff, and also sensing everything from oil pressure to intake air pressure, different exhaust stuff. There's just a whole bunch of sensors in an engine. It's nuts. So from that, it's going to periodically just be sending out messages, and they're all broadcasts. So just whoever decides to pick them up gets them. And in this case, I said, okay, we'll send this ID 123, and we packed the first 2 bytes with some useful stuff, and the rest is dead beef for fun. And the whole idea here is that beforehand, whenever you actually write the code that goes in these controllers, you have to agree on what byte means what. And you have a database file, essentially, that says what means what. And you would kind of assign some bytes to values. So in this case, you might say, okay, bytes 1 and 2, the endianness is this way, and it's going to mean engine RPM. You could also say things like, to get to the real world revolutions per minute, you need to multiply by 2 and subtract 6 or whatever. All that's set up beforehand by the manufacturer in these CAN database files, and those are pretty proprietary. They won't give it to you unless you're actually a vendor they work with. And in this case, they broadcast that message. Your instrument cluster picks it up, and then it takes that and eventually converts that into a command for a little servo motor to move your RPM dial. And that's a really simple example. Now, it also leads to another pretty simple attack, which is these CAN buses are totally trusted. If you send stuff on them, everyone will just assume you're supposed to be there. And all the traffic is visible to everybody. It's all broadcast. And also, any controller can send any message with any ID. Kind of like a MAC address, you can spoof. You can still spoof any ID on CAN. However, because the ID is directly correlated to what the data means, you can do some intentional spoofing. So if you had some rogue controller, you might be able to say, send a different value. In this case, 1F40, which is 8,000 RPM. And we're using the same ID, we're padding it with the same stuff. And the key here is if you send it faster, you'll probably win in most systems. They do some filtering, so usually whoever's faster wins. If you send the messages at the same time, it's actually sort of strange. Whatever for every bit in the message, if there's a 0, the 0 always wins. So that's just how at an electrical level it works. So you can inject stuff, and if you have more zeros, then you're the winner. So you do something like this, and you end up getting 8,000 RPM on your cluster, which is kind of fun. By the way, this car had no engine in it when we did this, so clearly it's being toyed with. Now, the injection thing, this is a really simple example. It's not terribly dangerous or anything. I spoke with somebody from one major company that makes automotive controllers, so the actual controllers that GM or Ford or whoever buy and put in their cars. And we were talking about this injection thing, and he goes, yeah, don't tell people to do that, because it actually is possible to destroy your engine by just injecting the wrong stuff, which I still haven't seen or believed, but the guy from the company that makes the engine controller said that, so I take his word for it. So yeah, that's kind of dangerous. Obviously, you can change, if one component is expecting an air pressure from something else and you fake that out, you might be able to just stall the engine completely. There's so many different things you can do once you're modifying these values, which is why the injection thing is kind of dangerous. So we've talked about 2 simple things you can do, but how do we actually connect to this system? You'll need some hardware and software. Hardware because MacBook Pros don't have a CAN bus port on them, so you'll need something to go to CAN. And in this case, most of them are USB to CAN, some are Ethernet to CAN, or even some ancient RS-232 to CAN, which don't do that because RS-232 can't even do the full bit rate that CAN needs to work, so those are terrible. And then you'll need some software, obviously, to do the send and receive and to encode and decode data in a way that makes sense. And you stick these things together and you sort of get some toolkits that let you talk to cars. Hardware, I did the sort of Yelp-style breakdown of hardware. Vector and Cavassar, for example, they're like the ones that target the automotive OEMs. You're looking at a lot of money, probably more than you'd want to spend unless you were doing this, for some serious commercial reason. The next level down, you're looking at Peak or Grid Connect. It's literally the same tool with a different sticker on it, or the Ecom cable. These are in the like couple $100 range. Going down one more, you have the open source stuff. So there's the Goodthopter and the Obduino. These are both open source designs that are based on the one microchip SPI to CAN chip that they have. The problem with these is you can't actually buy them. You have to have a board printed and then get it and then buy all the components and then solder it together yourself. So if you enjoy surface mount soldering, then that might be an option for you. If you don't, I've actually worked on this CanTac thing, which is a new open source tool. I have one here that goes from USB to CAN and also is assignable for pins, so you can plug in this guy if I can figure out how a DB9 connector works on stage. And you plug straight into a car, and you can get stuff right out of it. It's kind of fun. But if you want to just play with cars and really invest zero time or money, there's these things called the LM327 knockoffs. Basically, this Canadian company, Alm Electronics, made this really cool chip that does all of the OBD2, which we'll talk about later, protocols. You can find them from China for scary cheap, so cheap that you're probably going to go, I don't know if I want to plug this into my car. We're talking under $10 here from Deal Extreme. But there are some well-reviewed ones on Amazon and stuff. So for $10, $20, you can get something that you can actually plug into a car and do some stuff that can actually save you money. Clear your fault codes, read fault codes, that sort of thing. Software side, you have all the proprietary tools, but we'll focus on not those. So the main ones that are on Linux, I guess, are SocketCAN, this CanUtils package, and vCAN. SocketCAN is, actually all of this is sort of now part of the Linux kernel and some kind of user space tools that let you work with it. Wireshark actually has support for CAN, which most people don't know, but it does. So you can do all the PCAP goodness, and you can show that. And this Canard tool, I wanted to write a tool that made it easy to do stuff from Python. I wanted a pun that involved CAN and something else, but Vector has already stolen most of the puns. So I was left with the French word, I guess. So yeah. The SocketCAN is the first thing to look at here. So basically, this makes a Linux system or any Unix system, look at a CAN device that's going to go USB to CAN or whatever to CAN, and make it think that that device is actually a network device. And at this point, you can use the standard socket API and everything you'd expect with a normal network device. You can actually have raw CAN sockets. And yeah, it's one of those things that people have played around with sockets a lot, have never seen, but it's there. And it's included in the modern Linux kernel. If you install the newest Ubuntu, it will have this. And it literally works if config can 0 up. That enables the device. Then there are the CanUtils package. If you're on Ubuntu, apt-get install CanUtils. And that gets you these things like CanSend, which is a really simple way to send a message. CanDump, which will just dump all the traffic to you in different formats or to a file. CanGen, which lets you just generate random junk. And CanSniffer, which is a neat tool that lets you visualize a bunch of messages all at once and watch how they change. So all those are pretty handy for doing some basic work with CAN. Wireshark, yeah, it actually does it. Shows up like you'd expect, but the really useful part of it is you can do all the normal filtering that you'd expect. You can do based on ID or length. If you're using a protocol that we won't talk about because it's not used in cars, but one called CanOpen, it actually has filters for CanOpen, much like it has filters for HTTP or something. And you can just save the whole thing to a PCAP file, send it to people, whatever you want to do. So Wireshark's actually, in some ways, a better tool than most of the proprietary tools that do this, even though it was never built to do CAN. So it's fun. And then there's the one that I wrote. So this is Canard Python toolkit for CAN. 4 main goals. One is to sort of abstract away the hardware so you can plug in, this or a vector tool or whatever you want, and it doesn't matter. It'll just work. Protocol implementation, so we'll talk about the protocols at the end here. Basically getting those done for you so you don't need to reinvent the wheel every time you want to send a OBD clear fault code request. Ease of automation, so it's Python. You can script it to do stuff and hook it into all sorts of other things. You want a web server that's going to talk to your car, sure, whatever. Python's good for that. And sharing of information. The idea being if you write a script in Python that can work with different hardware, it should be easy for you to send that to somebody and they can then use that maybe with different hardware but on the same car. So hardware abstraction, really simple. Basically, a hardware device that talks CAN is just a class, and it's got 4 methods. You start it, you can stop it, you can send a message or receive a message. So really simple example, we create a socket CAN device with the name CAN0. So we'll have already plugged in and loaded the driver for that, and we'll have a CAN0 device. Start the device. We'll create a CAN frame. In this case, we want to have ID 100, data length 8, and just 1 through 8. It's a useless frame. Then we'll send it. That's pretty simple. And then we'll receive a frame, and that's actually a blocking receive there, so it's going to wait for it to get any frame back, and then it will stop. Really simple, but those 4 functions are really all a hardware device actually needs to do. So that's the basics. So from this, we can go back to the denial of service attack and do it in real code that actually works in one slide, which is nice. So we import some stuff. Cool. We create a device. In this case, because socket CAN is meant to be really generic, it doesn't have support for some of the more advanced features that you'd expect to find on a CAN controller, like hardware level filtering or acting in silent mode where it won't acknowledge anything. It'll just listen passively. So because of that, I created a different class for this CANTAC device, even though it works with socket CAN. You can just choose which one you want to use. So we create that, we start it, cool. Then we create our payload frame, which literally is just zeros. It's got an ID of 0, it's got 8 zeros, it's just a bunch of zeros. And then while true, send it, and your car will have check engine lights and probably different things dinging and all sorts of bad stuff. Don't do this, by the way, I don't recommend it. But since, breaking your car is only so much fun, we should probably talk about useful things you can do and how you can actually fix it if you did not take my advice and ran that code. So there's 2 main diagnostics protocols used in cars today. One is OBD2, one's Unified Diagnostic Services. OBD2 is actually a subset of Unified Diagnostic Services, but they're kind of separate. OBD2 comes from these folks at the California Air Resources Board. The whole reason it exists is because they wanted to be able to smog engines and kick cars off the road for polluting too much. That is the whole purpose of it. So don't expect to get too much useful information that's not about engines out of it. It will give you things like engine RPM, MAP or MAF pressure, vehicle speed, throttle position, all the engine things you'd expect, and not much more. The useful parts for you if you own a car is you can read and clear fault codes. It's a little limited in what you can read and clear, and you end up getting sort of a 16 or 2-byte code, and then you go on Google and try to figure out what that means. But I have had cases where someone's got a car that's not working, and we run that, and it says, oh, your mass airflow sensor needs to be replaced. So we just plug in a new one, and it works, and save them $1,000. And then clearing the fault code is kind of nice if you have that annoying check engine light that will never turn off. I'm sure some people here have a car that has that light stuck on. Maybe you've put electrical tape over top of the dashboard so that it won't shine in your face at night. So yeah, you can clear those codes. If something is still wrong with your car, it'll turn on again. So that's too bad. But at least you can find out if something is actually wrong, because some fault codes latch and have to be reset by a mechanic, whereas other fault codes are just kind of temporal. If it's happening, it'll stay on. If not, it'll go away. So clearing it can be handy. But that's all I can do with OBD2. It's only so much fun. Unified Diagnostic Services is where the real fun is. I'm going to call this UDS from now on because that's really a mouthful. But this is an ISO standard, which is probably why it has such a long name. It's ISO 14229 if you care to go find the PDF and pay ISO a bunch of money for it. But it allows diagnostic access to controllers. And what this is meant for is everything OBD doesn't cover. And that's everything from when the manufacturer sets your car up during like end-of-line manufacturing to when you take your car in for service and they maybe, I don't know, reset that oil filter change thing that tells you how long it's been since you changed the oil filter. And because it's an ISO standard, we might not know all the details about how it works for a specific car, but we can kind of generally get a framework for sending and receiving stuff over this standard. It's really simple how it works from a kind of network perspective. A client, which is some device you plug into your car that is not normally there, sends a UDS request. And it sends that to a server, which this is their terminology, not mine. The server is the automotive controller, so maybe an engine controller, body controller, whatever, seat controller. Yes, cars have individual controllers for seats. Then you get a response back, either a positive response or a negative response with either your data or a fault code or whatever it is, and you take that and figure out what to do next. There's a bunch of different services, and these are just like the really cool ones. There's a lot of different ones. Security access is one that's really broken. They use this to try to secure some of the more important features, things like changing, manufacturing stuff, VIN numbers, that kind of thing. There was actually a talk, or a paper rather, back in 2011 from the folks at University of Washington's Automotive Security Research Group, and they basically found that this thing is broken in every car, and we'll see how in a minute. But they were the guys who figured that out, and it's bad. But that's one of the services. Routine control. This lets you do everything from like roll the window up and down, honk the horn, apply brakes in some cases, just all sorts of different arbitrary routines. It's super arbitrary. You literally pick an index and something happens. I've been told that this, well, I've never seen it, but someone was daring me to do this on an airbag controller and like try every routine. I don't have the guts to do it, but maybe it would do something bad. But the point is there's a lot of functionality that you can actually expose just by doing these routine control requests. So the read data by identifier and write data by identifier, these are things like a VIN number, an oil pressure, both readable and writable stuff, stuff that's going to be read-only because it's temporal, like an oil pressure, other stuff that's going to be secured so that you can only write to it if the car is in security access mode. Then you have also read and write memory by address, and apparently in some vehicles this is still enabled in production, which is scary because you can literally just like get a memory map of the controller by running through every address. So yeah, that's a feature that I'm not sure exactly what the purpose of it is. It makes sense in development, but no, shouldn't be turned on at the time where you're dealing with the car, really. So yeah, this library is also going to provide you some help, I guess, for doing UDS. Still a little bit, not as high level as I'd like it to be yet, but we're getting there. So we import some stuff, cool. And then we're going to set up a device. In this case, we're using sys.argv1 so that we can choose a device that we want to use at the command line. We're going to set the bit rate to 500K. 500K is what you typically see in cars for high-speed CAN buses. Some are different, but usually it's that. If you really want to know, you can like stick a scope on it and look for individual bits and figure it out. And then we just start the device. And then we're going to create this UDS interface. This is going to essentially wrap around our device and just provide us with a request response. And because all requests are initiated by the client, which is whatever's running this code, it makes it nice and easy because we can just go, hey, I want a request, and get a response. So what we're actually doing in this example is pretty useful, actually. We're going to try to find all the controllers that will respond to a diagnostic request so that we can enumerate all of them. In the case where you're plugging into that OBD port, you might only be able to see certain controllers, and other ones you might have to send messages that end up being gatewayed through various CAN buses to get to that final controller, then the messages come all the way back. So this lets you just run through and see who's out there and kind of knock on the controllers and see if they respond. Pretty simple stuff. We just go through from OX700 to OX7FF, which is the last CAN ID. Then for each one, we're going to do a UDS request. This is the little bit of a cryptic part if you haven't seen the spec. Basically, we're going to do a request on the ID that's I, We're requesting service OX10, which happens to be diagnostic session control. Then we're going to send a payload of just OX1, just 1, because that is just put me in diagnostic mode 1, please. And then we'll set a timeout because we don't want this to go on forever if the controller is not actually responding. And you do that, and if you get a response back, you know, a valid UDS response back, you know, hey, this is actually a controller that's going to be using this service and we can actually try other stuff on it. I did this on actually my roommate's car because I wanted something different. He has a Honda, which I haven't played around with much. And I immediately was able to get out, okay, there's one controller that responds on the OBD port, and it's OX740, and from there I could start doing like ECU resets and read data identifier, all that stuff. Pretty simple example, but it fits on a slide, so and it does something useful. So security access. I like talking about this just because it sort of sums up the theme of security in automotive, which is it's not great. So this is done, there's a number of reasons they do it this way, but we'll go through how it works first. So the idea is there's certain things that they really don't want you to do. One of them is upload firmware to a controller, because being able to modify firmware on on an engine seems to be a bad idea. And modifying things like odometers, VINs, other things that are probably protected. Even engine calibration values maybe that would change the operation of your engine. One thing that's worth noting, automotive companies, basically they optimize for emissions and only emissions nowadays. Performance they do in their performance vehicles, but emissions is what they really care about because of some new requirements that the vehicles across their fleet maintain a certain level of emissions. So yeah, people want to reflash stuff because they want more performance and they know their car's been kind of nerfed a bit to meet the emissions requirements. So they don't want you changing those things. The way that this works, it's like a really simple seed key exchange, which you've probably seen before for stuff on not cars. Basically, the client's going to request a seed. The server will send one back, and based on that seed, it will generate a key. It sends that to the server, and it comes back with, hey, you were either allowed in, or no, that was an invalid key, or you've tried too many times, sorry, don't try again. Doesn't look so bad at first, but the problem is that the seed is fixed for that controller. And so that's the first kind of red flag, and that means that the key is also fixed. Now, the reason that they do this is because, or the reason that they say they do this is because they can't generate good random numbers on the controllers, which is, I guess, fair. I mean, there's probably other stuff they could have done, but that's their rationale. But this in itself is even going to be like just a pain if you don't have access to the controller, if you can't dump memory. The real problem is that they're only 16 bits long, so you can brute force the key space in not that long. It ends up being that you get locked out after a few tries, but you can just reset the controller and continue trying because they don't have any non-volatile storage for that type of thing. They have some controllers have a delay from the time where you turn the controller on to when you can start requesting this, which actually, if you read the guidelines, like that's the recommended thing to do, is just wait 1 second to prevent brute forcing. But with 16 bits, you can still do it in like a matter of days if you want to take over a specific controller. So it's not great. And then this is why it's a little broken, but the really bad part is in some cases there's been like DLL files that come with upgrade tools from people like Ford, specifically Ford, that end up containing code that actually just generates the key given a seed. So, I mean, you only need it once. There's only one algorithm in there, so once you have that, you're pretty much good to go. Some people have been able to extract those types of things. So that's also bad. So the whole idea with this diagnostic stuff, and we have a little bit of tools to talk to it now, is we can fuzz. We can do this automated controller discovery thing by just hammering all the different IDs. That's a start. But we can do some way more complex mapping. We can actually read all the identifiers and all the memory addresses it'll let us read. We can try running every single routine, which is the thing that would be scary on an airbag controller. Literally, from 0 to FFFF, do something, and you'll find out when it happens. We could also get the memory permission so we can try writing and see if it fails, and if it does, we know, okay, that's only readable. And obviously, we can do things like brute force security keys. And a lot of this stuff is just left open, so pretty much anything you can think of, you can write a quick script to be like, hey, I want to read all this stuff out, or I want to try to try to modify some values. You may void your warranty. I mean, that probably should have been in my first slide, but yeah, this stuff is meant to be accessed by a tool that's external. That's the biggest difference. Is there actually are tools you can buy that will plug in and do this. The problem being that they're expensive and they only have a very limited subset of all the diagnostic actions you can do, because Ford doesn't want to give every mechanic the ability to change the VIN number of a car if they don't have to. So that's where it really comes in, that you can start to reverse engineer these and figure out what they are. So yeah, the little conclusions on what we went over here, and then we'll have some questions. Basically 3 simple things you can do to a CAN bus that all work pretty well is you can do a really terribly easy denial of service attack. You can do injection on the car, and change things that are running, maybe destroy an engine according to some people. And then you can do these diagnostic actions, and that is a whole software stack that who knows what you'll find in there when you start to go looking. You can access it and modify stuff as you're supposed to, but who knows what else you'll find. And another concern is that these attacks, any device that's on your bus can do this. So if you have one of those, I think Desjardins has the little device that plugs in, and it records stuff about your driving and then gives them your data in return for lower insurance. That's kind of concerning for a lot of privacy reasons, like I won't even go into, but potentially they could also take control of parts of your car, so you're signing that over too. And a little concerning. And then the other thing is you'll need hardware interface and software tools. I mean, if you want to do CAN, I'm partial to my own, this CANTAC device. But if you just want to play around, for 10 or 15 bucks to buy one of those OBD Elm 327 things, it'll work on any car past 91, so you can have some fun. Only thing about those is you probably don't want to buy the Bluetooth versions, just because if you leave that plugged in, you're sort of asking for it. And then the software side, you have all sorts of stuff, but the open source stuff, there's the library that I've worked on, and also some other, there's actually a Ruby library as well, if you prefer Ruby, that does CAN. There's a lot of different languages. People have kind of hacked some stuff together. CanUtils, if you want to play around with that, you can actually install it on Ubuntu, and using the vCan driver, you have to mod probe vCan, but once you get that up and running, you can send messages around in memory, so you can play around with these tools without actually having a car, without having a hardware interface, if that's something you want to play with. And Wireshark, you can also connect Wireshark to anything that's running and just watch, which is very useful. I have no time up here, so I don't know how I did, but thanks for coming, and hopefully it was an interesting thing to listen to, and I think we'll have some time for questions.
Yeah. We do have time for questions, so